finishing the three models of memory that I said, and this is the one that we have already covered. I mean, introduced in the last class, which was called the which is called the Atkins and Shiffrin model, because Atkinson and Shiffrin proposed this model, and this is the simplest one among the simple ones. And it is called three store model because there are three different storage. This model views memory as a storage of information. So you take stuff and you store in it. So that's what memory, and that's a very commonsensical understanding of memory also, that memory is more of a storage of information, a storehouse of information. So here it says there are three stores. One is a sensory store, which has multiple registers for the different sensory inputs that is going to come from the environment. Then you have a second kind of store, which is also called the short-term store, sometimes also called temporary or working memory storage, which has different cognitive processes, mainly to do with rehearsal of information. So you have information coming in, you rehearse that information, read it or memorize it or whatever, similar to stuff that you do for all the exams. And then depending on how much you have rehearsed, some of it goes into your permanent memory store, and others remain in your working store, and then you forget about it. Similarly, if you require to retrieve information from your long-term memory, or also sometimes called a permanent memory store, this information, that's why you have an arrow back to your temporary memory. And eventually, you create a response. This response can be an answer that you give in an exam. It can be a sentence that you produce. It can be a thought that occurs to you. Any kind of response is fine here. So because this proposes that we have three different kinds of storage, it's called the three store model of memory. Okay, couple of important points. Please note that the storage that is proposed here is abstract. So you won't really find one-to-one mapping in the brain for each of these storages. So they are hypothetical constructs, more like models, mathematical models or mental models, ideally. Most important thing that you should remember is this memory model treats of memory to be more like a passive storage. So information is coming, you're storing it in memory, or rather it gets stored in memory is the precise correct way to put it. Um, it also has no introspective access to sensory store, which means that I cannot understand right now, even if I try, what exactly is being stored in my visual sensory register, because it's so fast and so small. I cannot have a conscious access to it, and hence I do not have awareness of it. Similarly, when I say a sound or a word, it gets stored in your auditory memory, auditory register, but you can't figure out what is the word that is currently stored in your auditory register. Any of you can try right now. It's basically impossible to do it. These are more examples, more information about sensory store. So the first thing that you could ask, and some of you have already asked, is what is the capacity of storage for these kinds of information? And the second interesting question to ask is how long is information stored in each of these storages? So for the capacity question, George Sperling did a lot of research around it um, in the Department of Psychology at Harvard. And the question here was, how much information can people encode when you flash very briefly? Now, what is brief? That also must be operationally defined, as I keep on repeating. So if you really want to build a proper science, or a decent enough science at least, of human psychology, you can't use abstract terms, or you can't use terms without defining them well. So here Sperling does a fantastic job at it. He says, well, flash essentially here is 50 milliseconds. So if you show something for 50 milliseconds, how much of that gets stored in my sensory memory is what he was asking for the visual register, visual sensory register. Okay, so how do you do it? Let me show you an example here. They will show these kinds of random letters on the screen, and They will flash the screen for 50 milliseconds, and they will ask people to recollect which were the letters that they saw. How many letters do you think people would be able to recollect if you do this task? Any hunch? And
2 or 3.
even better if you can say why you think so, but at least the hunch of how many. Here you see, 4 into 3, which is 12 letters, and these are random letters. And I flash that for 50 milliseconds on the screen, and I tell people immediately after that, all right, immediately after that, to recollect as many as they can. How many do you think typically the average number that people would be able to recollect?
1 to 2 column of the given figure, maybe
1 to 2?
columns of the given figure, like 6 letters according to me, max to max.
I guess 4.
1 to 2 alphabets.
1 to 2
Yes,
letters.
most
So it
probably 1 to 2 letters.
One row or one column.
Sir, are we talking about the location of each letter or only the letters?
only the letters.
Okay, then 4 only. Yes.
So people told that they will be asked later on.
Yes, they are told.
Okay, so I think 2 to 3.
All right. So, the questions that you all are asking are very interesting because Perling himself had done all these manipulations. He did a couple of studies by telling participants that they will be asked. He also did a couple of studies, and he and many other people, where participants did not know that they will be asked. So, okay, right. So what is the difference between being told and not told based on what you have already studied? Which process is at hand here?
Attention.
Perfect. Visual attention, in what form? I talked about attention of multiple, because attention itself is a very big word. What aspect of attention is at play here?
Inattentional blindness. I should.
You could manipulate it. Well, you can show inattentional blindness perhaps by suddenly flipping something on the thing, but we are saying of attention. Let's first fix that before we go to inattention. So attention, you can talk of attention different ways. I said that is selective picking up of information, so it's called selective attention. You could also think about attention as having resource. You can think of attention as scope, which is a broad scope or a narrow scope. So out of these three, which is the one that is most pertinent here? Attention for selection of information or selective attention, number one. Second, attention as a resource of holding information. Third, attention as a scope, which can be either broad or narrow.
Selective attention, because we are just focusing on the visual perspective, and we're not.
Great. So then the next question to ask is, will people remember individual letters or will people remember individual columns? And I think you all had answers from both. So could any of you say what is your, and both of them, one answer about what is the hunch for that? We say individual letters, 1 or 2 letters, versus somebody who's saying individual columns, like 1 or 2 columns. And again, any previous stuff that we covered in class that helps you think through this?
Sir, so like for example, in a movie, the frames are 16 frames are shown per second. So that is, if we show it for 0.05 seconds, we will be able to not form a pattern like see a column. We will be only focusing on minimum area possible. So that will be like a corner or maximum 2-3 letters.
Yeah, that's also because your foveal vision is small, right? So wherever you are attending to, whichever random part of the screen is where you pick up the information. That's your hunch. And that typically, looking at this kind of screen, it's about 1 or 2 letters. Okay, that's a good one. Anybody who was saying columns? Why, how one or two columns?
So I think we will be able to remember columns because we will be able to relate them with each other. Like HAE, we can just make a word out of it and we can remember all the three letters.
Oh, but this is 50 milliseconds, no?
But I
If you
still
repeat for
think
a
that,
second, yes.
like even for a millisecond, that I think we can still make a even a senseless word out of it. Like yeah, it depends where we are looking at that point of time. If we are in a way that we have to remember all the words that will be uh, we will be shown on the screen, then I think we will be able to remember column wise instead of individual letters.
All right. So let's see what the results show. So first of all, okay, by the way, so this whole thing is being done to answer this question. How much information can people encode in a brief flash? Remember, every good research has one fundamental question. Most, not every. So this is Sperling's fundamental question. To achieve an answer to this question, this is the kind of task he has come up with. So this is the result. So typically, most people report 4 or less than 4. And then, well, that time it was the time of behaviorists, so people really did not believe asking people much. But still, Sperling asked people, do you think you saw more than 4? Most people say, yes, I saw more than 4, but this is all I can remember. Maybe 2 letters, maybe 3 letters, at most 4 letters. Now note that 4 letters essentially is 1 row, 3 letters is essentially 1 column. So technically, you could remember 1 row or 1 column, but even though you have this hunch, people were not able to do that. So the reports that they were giving were spread across. So sometimes they would be from a row or a column, sometimes they would be spread across multiple things. Especially if you focus your attention in the middle of the screen, which is between H and M, let's say here where I'm showing my cross, then probably this will be your foveal vision, and this is what you are going to pick up. If you focus your attention here, then this is what you will pick up. If you focus your attention here, this is what you will pick up. So where you will focus your attention keeps on fluctuating for every trial, every time this task is run. And this is typically run on the same person about 30, 60, 90, 100, 20 times. Now, what he did was a slight manipulation, which is that he introduced an additional arrow. So let me see if I can play this thing. Okay, so this would be flashed, and then this arrow will come, and then it's going to go for a very small amount of time. What happened was, once this arrow queued a specific row, then most people were able to recollect this row. Then this would be random. So sometimes the arrow would come on the last row, sometimes on the top row, sometimes on the middle row. Whichever row queued, the word is CUE. Q. Q means giving a pointer. Whenever the arrow queued a specific row, then people were able to recollect this row. What does this show? How much information are we actually able to hold? Is it 4, or is it 8, or is it 12?
1 to 4.
Yes, 4 we are able to hold. You are right. But I mean, I hope you have not read Miller anywhere and said this. Miller also said ±4 as a magic number. Sorry, ±7 as a magic number. But we'll go to that later. Yes, yeah, here it seems 4, but remember that this arrow can come at any place. So you technically do not know where the arrow is going to come. Wherever it comes, or wherever is the queue, you are able to pick up the 4 from that queue. What does
So
it say?
I think our vision will go to the arrow and it will be narrowed in that region. So only the letters beside it, like E and maximum A, can be captured by our vision.
Yeah, but see, what he was trying to get at is he's saying if you tell people to report all the letters, then people are able to report up between 1 to 4. But what if I ask people to report a small sample? That's what he called a partial report, not a full report, a partial report. And the partial report is queued by the arrow. So last row is a partial report of the whole thing. Middle row is partial report of the whole thing. Top row is also a partial report of the whole thing. Now, what his argument was that if people are, okay, let me say these things also. If people are able to recollect whatever, irrespective of where the queue is coming, then it shows that people really have the information available in their head. They simply cannot report it. So he suggested that, well, essentially the information is there, but whatever people report is more constrained or constricted. So people have 9 or 12 information or the items in their sensory store, but they can report about 3 to 4. And his rationale for that kind of an argument is that because the arrow is random, there is no way I know beforehand that this is, this is the row I have to remember, or this is the row I will be checked for. So sensory store is something which has higher capacity, and according to him has a capacity of 9 to 12 items. Here items is digits, not strings of digits. But whatever you are recalling is a smaller subset of that. It's a much smaller part of what is actually stored in your sensory register. What he also did was he manipulated when the queue is going to come. And I hope I have a graph here. Yeah. So he showed that if you delay the queue, so here at 0, this is no delay. Okay. If there is no delay, then people can report a large number of items. But if you increase the delay, so if after the thing is shown and then after a while you show the queue, and eventually you increase the time difference between the queue and the stimuli to up to 1 minute. Sorry, up to 1 second. Then people start performing at chance, which means that they are guessing. So 50% chance basically means that there is no surety of the answer. You can't trust the answer. So once there is a big difference in time between when the letters were shown and when the queue was shown, then people are really bad at this task. But if there is no delay, or if there is a very small delay, or even better, if the queue precedes, which is when I already know that this is the stuff that I have to remember, then actually the number of items, the number of letters recalled can go up to very high. So what you were getting in the initial part when we were asking people for a full recall or a full report of all the letters was that you were getting about 4 letters or so, which is what happens when you have no effect of the queue. Because if the queue comes much later, then it's, it has already faded from your sensory memory anyway. But if you introduce a queue, you can show that your sensory register has much higher value than what previously people thought, which is what the same thing that you all were saying, between 2 to 4, or yeah, somebody said 6, but typically it's between 4 to 5, or 4 is a good number. But it's not the case, because the problem is it is separating out what is actually stored in your sensory memory versus what you can recall from your sensory memory. What you can recall is 4, But what's stored is much more if there's a cue that is introduced. It can be by a sound or it can also be by a visual cue. Okay, so that is that was a great finding at that time.
Sir,
A classic one. Yeah.
sir,
Questions?
how in the short duration of the time number of letters recall are higher than the number of the letters recall at the more time?
Yeah, because what he's doing is basically multiplying. So multiply the number of symbols recalled by 3. Because the answer that you're getting here is basically after multiplication. But your question was something else. What was that? I'm sorry. How are we getting what?
So my question is that on increasing time, number of letter recall should be increased, but there is a reverse trend.
No. You're not increasing time. You're increasing the delay. So this thing, I'm sorry. Why is it? Yeah. So what he is saying is this is your stimuli and this is your cue. The delay between showing the stimuli and showing the cue is what you're increasing. If it happens at the same time, it's a 0 millisecond delay. Do you keep on increasing the delay till it becomes up to 1 second? And the finding and the empirical finding is that if you increase the delay between the cue and the stimuli that you are showing, then the number of items that you are recalling is going down, but they probably are there in your sensory memory. You simply cannot recall them. That's why I'm saying there is a difference between encoding, storage, and retrieval. What was happening in the whole report was typically people were reporting up to 3 to 4 numbers or 3 to 4 letters. He is saying if you introduce a cue and that cue happens very quickly, either preceding or very quickly, so this time. So you are really talking about 7 to 10 items or 7 to 10 letters that people are able to recall, because you're multiplying the number of items that people are recalling with the number of rows, essentially on the presumption that because the queue is random, you can technically not know where the queue is going to come. So automatically you are needing to store all the 3 rows because you don't know which row you will have to recollect. And same thing you can do with columns also. But if the queue goes to is delayed for a long time, then by that time the sensory register is faded away, and hence you are reverted back to your baseline performance, which was about 4 letters, which was happening for the whole report. So the effect of the queue, goes away if it's delayed. So it's the delay, you see, delay of tone or delay of the cue in seconds. Delay between the cue and this thing. Is it clear now?
Yes, sir.
Great. All right, so then the next thing is short-term store. Now here again, you can ask the same question: how much is our short-term store? And George Miller has done phenomenal work in this, and he concludes that it is 7. And see how psychology was much more well defined than what you think psychology is. And that was, a couple of people at that time did fantastic work in quantitative psychology, where they wanted exact answers, not like, oh, I forget things. They would say, how long does it take for me to forget X number of things? That's the precision in which people were working. And again, people do work now also, of course. Some subset of psychology does that. Typically, a lot of cognitive psychology or mathematical psychology does that, but not all areas of psychology. But anyway, so here the question is the amount of information, and that is 7 items. Now you can ask, what are items? So Miller said 7 items plus minus 2. So Miller is saying, well, between 5 to 9 items, 7 is more of an approximation. Now items, initially Miller used the word items in the same way as number of letters or number of digits. But eventually people figured out that it's not just alphabets or digits. You can even store strings, what they call chunks. So if it's, if you break up your stimuli or break up your alphabet string into smaller size of three letters, or if you break up a large number into 3 or 2 or 4 letters, 2 or 3 or 4 numbers, then 7 such items is what you can store in your short-term memory, according to Miller. Not 7 technically, between 5 to 9. Some people have lower capacity, so they might be able to store up to 3 or 4. Some people have very high capacity, they might be exceeding 9. But typically, for most adults without any disorders, the number is 7 and ranged between 5 to 9. How long? That question Miller asked, and the answer is it is basically between few seconds to a few minutes. Whereas your sensory register was a few, less than a second, I mean, essentially few milliseconds. What happens? Well, essentially you have control processes that help transfer some amount of information to the long-term storage. But what happens if you don't rehearse? Well, it essentially fades away. So it stays for some amount of time and then it fades away. The initial classic studies were when people were told random strings of numbers, like telephone numbers of 10 digits or 12 digits or 15 digits, and they had to recall them after a few seconds. And that's how you come to know how much time it stays in your memory. Typically, it doesn't last up to a minute for most people. However, this is the idea that I was talking about. You can break things up. So you can think of these as individual items. 1 is an item, 0 is an item, 1 is an item. Or you can break it up and say 101 is an item, 00 is an item, 1000 is an item. If I break up this random stimuli into smaller chunks, chunks, then you store this chunk. So here you are storing 1, 2, 3, 4, 5, 6. 6 chunks of information. And hence 6 items of information. So item can be a chunk, is the point. Obviously, it depends on what you are being fed. So sometimes it's easier to make up structure, sometimes it's more difficult. And here again, if you have any delay, then the number drops to 4. So 4 is a very good number that you can think about. Interestingly, more follow-up studies were done. And once you bring in this idea of more complex stimuli, especially stimuli which has items or different chunks in it, then Cowan, who did a lot of work on working memory, more contemporary work, showed that the number is not really 7, the number is 4. So typically, it's about 3 to 5, which is some of the hunches that you had, and you had the correct hunch. Generally, it's about 3 to 5 items. Randomly is what people are able to store, but now we are talking about short-term storage, please. We are not talking about sensory storage. My question was about sensory storage. Both for sensory storage and for short-term storage, it seems that if you don't do anything else, 3 to 5 is what most people get at, as far as quantity is concerned. Now, how much can you store in long-term memory? We don't know. That is the non-honest answer. There are different estimates. So some people say millions of gigabytes. Some people say, some terabytes. But these are estimates. We don't exactly know a very clear answer on this. And one problem to know the answer is we don't know how to measure it, because by definition it's long-term storage. So how do you really measure how much information is stored in our brains? How long can it be stored? That again is unknown. There are studies on memory disorders where people have forgotten certain things, But for normal population, it's not quite clear how long a memory lasts. It depends on the value of memory, as I have already pointed out. It also depends on the emotion associated with the memory. But the precise answer of how long, as you get for sensory storage and for short-term storage, we don't get for long-term storage. And to think about it, think about, let's say, a photograph that was taken long time back in school when you were in class 1 or 2. And how many of these names can you remember? Friends' names can you remember after, let's say, 20 years, or if you all are younger, 15 years of the photo being taken, or even 10 years from the photo being taken? Or think about it this way, if you take a photograph of your class, how many names would you be able to remember 20 years from today? Any hunches? Imagine you have, let's say, a large class, okay, so 200 people or so. How many of that would you remember? Names would you be able to remember?
So generally those we will remember the generally those names 10 or 12 maximum. I'm saying those which have the contact with them for the long time, or we have those have the friends at that time, not the whole
Yes.
class.
Okay. And would you remember that all through your life?
No,
2-3
only,
people maybe.
only those which have the contact with them regular continuously in our life.
No, it's better than 2, 3. I mean, um, I'm sure most of you all have better memory than me. I don't really have good memory. But still, when I see a school photograph randomly taken when I was in class 5, which was, when was it? 1995, year 1995. That day I tried this exercise, I could recollect about 17, 18 such names from school. And none of them I have any contact with for the last 10 years, at least, maybe more. So probably it's more, but the point is it's hard to measure it. That's the thing that I was wanting to point out. And that's the one problem of measuring information in long-term store. However, some of you think that you might remember one or two places, one or two names all through your life, which is why some people also think that long-term storage is actually permanent storage, or perma-store, or permanent storage. We somehow don't forget some of the information all through our life, unless there is a memory disorder or some other cognitive disorder. So that's why technically it's kind of infinite. However, having said that, the 3-store model is pretty limited in the way or the stuff that it can explain, and it takes a very passive view of memory, thinking that memory has a storage and it has these different 3 kinds of storage. So more work was done, and now they had a different kind of way to think about memory, which was they thought that memory is more like a process. It's not a storage or storehouse of information. It's more of a process of processing information. So they came up with levels of process models of memory, and this is based on encoding. So how much or how deep you encode the information is how long it's going to stay. It's not about where you store it. It's about how you process the information when it is fed to you. Now, you can ask how many levels are there for encoding. There's already an answer. Theoretically, it's infinite. But obviously, for practical purposes, it has multiple levels of encoding, and they are finite, maybe about 3 to 5 such levels. Now, what happens when you encode information is that you elaborate on it. And I will give you an example so to cut this abstractness here. But what's important is information processing is the key to storage. The more you process the information, the more it's going to be stored for a larger amount of time. This is predominant for learning, and class learning or student learning, because what you store in your long-term storage is going to happen at the time of encoding. And it's not one single time. You can encode multiple times. You can read the same text multiple times. Every time there is some kind of encoding that's happening. But every time you might not pay the same amount of attention. Every time you might not elaborate as much as you are doing at certain instance of time. Depending on how much you elaborate, if you elaborate more encoding is going to happen, and more processing is going to happen, and more long-term storage is going to be the outcome of it. That's how levels of processing models think about memory. And automatically, this defines that the probability of recall, which you can actually define with some kind of very vague probability function, is going to depend on how much you have processed the information at the encoding stage. All right, so here is an example of levels of processing. So imagine that there are 3 levels of processing. Theoretically, it can be infinite, but for our sake of argument, let's say there are 3 levels of processing. And one level of processing is mainly at the visual feature. So you really are not paying too much of attention. I have to remember the word table. The only processing that you do is to look at the form table and say, oh, is it capital or small? All right. So this is a pretty superficial level of processing, which is the physical level of processing, which is mainly to do with physical properties of whatever you have to remember. Then you can go one step further and do more processing about forms. Here, this is a phonological form, sounds. So let's say I have to remember the word cat. You figure out, oh, does it rhyme with mat? Over and above, acknowledging that CAT is written in capital letters. So if you're thinking more about this word, maybe about the rhyme, maybe about what other stuff that rhymes with it, or how does it sound, this is phonological level. Then you go further deep at the semantic level and you focus on the meaning of what you're learning. So daffodil here, for example, is a word that you have to remember. You ask the question of, is this a type of a plant? Is this a type of a flower? Is this a type of animal? So you're doing more deeper processing. Every single concept, if you think of that as a word which you are written down, you can process it in these multiple levels: physical, phonological, semantic, and more perhaps. What it turns out is, this is work done by Craig and Tulving, who are again great psychologists who have worked on memory a lot and also worked on models of memory, say that if you force people to either use a semantic level of processing, or you force people to use only a physical level of processing, you can see that the recall is highest when there is semantic encoding, or when you understand the meaning of something. All right, quick question. What is your learning lesson from this about how the memory works, both the short-term, long-term, and sensory registers talk, and the levels of processing talk here, where you have different levels of processing the same concept: physical, phonological, semantic? What's the learning lesson if you have to apply that to your own learning? Was my video off? I don't remember. Yeah, probably it was. Okay. Yeah. Who wants to try? Go ahead.
So semantic.
So what's the learning lesson? So what is it that you can take home from here about the way memory works, and you can apply that in your own learning, practices or habits or whatever?
So it suggests that if we understand something, then there is a greater chance of us remembering it for a long time.
Can you repeat that? I don't think everybody heard that properly.
Hello?
Yeah, go ahead.
So I was saying that it suggests that if we understand something, then there is a greater chance of us remembering it for a long time rather than just superficially going over it. Like just in case of studying as well, like reading it for once, like okay, I'm going to write it tomorrow, and that's it. But if we rather focus on understanding the concept, then there is a greater chance that we would remember it for years.
Yeah, that's true. But then that is something that is also commonsensical knowledge, right? So we have been told right from our school that if we understand something, or rather, we should understand a concept that helps us remember us more. So what is new information here? You're right, but this is also something that we already knew beforehand.
So I think rehearsing what we have learned will help us recall it better. So this is something more to add to it.
How would you rehearse?
Uh, by applying that concept again and again.
Okay. I mean, you know this word called ratta, right?
It's not that actually.
You are in the right direction. So think a little more. I mean, maybe here one or two other people, then you can come back. You are at the right, but I'm just trying to push you, both all of you, to think that beyond what already we knew or everybody talks about in society, what additional stuff can I take home from these kinds of psychological classes? There's something more.
Sir, we can also try to do the three types of encoding, like physical, also by looking at how the word looks and comparing it with the other words and then understanding its meaning. So it might help.
All right. So, one hint: try to mix both the models. What you learned, or what I presented on the screen regarding the storage model and the processing model. If you merge them, there are new things that you can do.
Then it would suggest that something which is learned semantically is stored in the long storage, in the long-term storage, and the others are stored in the sensory or in the what it is, intermediate part. Hello.
Yeah, I mean, I heard some part of it, but not everything very, very clearly. Um, I heard the part about semantic, but I didn't really quite follow of this mix between these things. Can you or somebody else try, or I mean, we can go forward, but just wanted to take a quick pause to appreciate what is new stuff here. See, what Craig and Tulving is saying is that they are giving you ways in which you can think about semantics, or they are saying ways in which you can think about phonological. If you remember, I mean, at least I used to mug up many of the historical events using some kinds of poems. There's a technical word called mnemonic, which is used in many of these exams, especially if you're preparing for GRE and all, or some kinds of other competitive exams like CAT or IAS and all whatnot. So most such exams ask verbal questions. And mnemonic becomes a good memory cue or memory aid that most teachers say might help you. So it's more like a way to remember certain things in a shorter manner. Any of you have used that before?
Yes, sir. In the generally in the inorganic chemistry, we have to use the mnemonics.
Mm-hmm. So how do you think mnemonics works? I mean, why does mnemonic make it easier for us to recall?
So it gives a hint which we have to which we can easily with the help of that recall the things. It gives a first letter of that thing, or the if there any reaction, or the color of the thing that gives the color of that. It gives a image of that situation which we have learned with the help of that mnemonic.
Right. You remember this slide that we saw in the last class about food on the highway, which was I said as an implicit memory task,
Yes, sir.
right? And you also filled up some other word. I forgot what we did. Yeah. So these are implicit memory cues. Mnemonics are implicit memory cues, and the also sometimes you rhyme or have a rhythm for uh, for learning. In fact, there are these very big holy scriptures, or um, or multiple religions have these big passages that people chant every day or whatever multiple times in a year, and they remember it, everything by heart. So a lot of that really is stuff that we are talking about. You can't do it from, let's say a very superficial physical level of processing, but you can do a lot through phonological. In fact, even if you don't remember or don't understand certain things, the meanings of certain things, or how it relates to other things in the world, remember that we talked about a semantic network in the brain where every concept is connected with every other concept. The same semantic network comes back here as the semantic level of processing. Semantic is meaning. So the ideal form of learning that is supposed to be long-term is through semantic encoding, which means the new concept gets attached to your already existing semantic network in your brain, so that you can relate that concept with any other concept. So think about what is happening right now. I am trying to relate a concept that we are covering in a psychology course related to do with memory, and you are trying to associate that with many other kinds of things that you are doing in chemistry, things that you are hearing, in society, maybe a movie um, where people memorize, let's say, the national anthem without understanding what the national anthem is, but they memorize it and they do a very good job at it, where you basically work on sound combinations, which is at the phonological level. So what we are doing right now is essentially semantic encoding of memory as a concept itself. Do you realize that? What, is it a shocker and everybody went silent? This is how you have to start doing, or not have to, you could consider start doing in many other things that you will study or are already studying. So one important aspect when you're studying about the human mind is to start using stuff of that in your life, not just reproduce them in the exams. Yeah, and that's at least that's one learning lesson I try to take whenever I learn something about how our mind works. Okay, so I'll give you the third memory model here, which is little more complicated than the previous one. This was given by Badley. It's called an integrated working memory model because Badley said, hold on, what exactly is a short-term memory and what exactly is a long-term memory? It is not clear. Badley also said, how exactly is rehearsal happening? Badley also said, we have multiple ways information is feeding in, and we have the role of attention and control mechanisms that is at play. So how do we bring in all that together? He said we have to integrate three major ideas. One, we have a high level controller which takes care of what is the information that I'm going to attend to, what's the information I'm going to memorize, and how I'm going to recall. That he called a central executive. If you look at inside the brain, this is more closer to your frontal lobe in your brain, which is also the attention well, not the attention. Attention is spread across the brain, but mainly to do with the, with control-based processes. Then the second part of this model has to do with where is information coming from. So we have verbal information, we have visual information, and he had hypothesized two different areas in which this is going to be processed. So he said the visual information is going to be processed in what he called the visuospatial sketchpad, and the verbal information is going to be processed in what he called the phonological loop. In the phonological loop, he's hypothesized two things. One is phonological storage, which means that it is based on sound. Whatever I utter, even when you're reading a text, you're reading line by line from a book, or you're hearing a lecture, or even talking to yourself. That is phonological storage. Subvocal rehearsal is when the voice is not coming out from your throat, but you are rehearsing it. No, it's in colloquial language what we say, talking in the mind. And all of us do that. Sometimes to memorize things, sometimes to remember things, sometimes just when we talk to ourselves, there is no voice that comes out, but it's subvocal. So there is actually a little bit of vocal activity, and people have measured that. You can pick up subvocal activity by attaching certain devices in your throat. It vibrates at certain frequencies, and you know that it's subvocal articulation happening. Rehearsal helps you to remember certain sounds that's coming in as verbal information. This is the second part of the story. The third part is he introduced a catch-all term, which is like an episodic buffer. Here, this is an episode. It binds information from phonological loop and visuospatial sketchpad into one single episode. It connects with the central executive, and it stores part of it or retrieves part of it from long-term memory. Episodic buffer is an integration device, or not device, integration process that enables you to store one single thing, right? So remember that we don't separate out the sound from the vision. When we memorize something or when we remember something, we remember it in its holistic way. If we remember a rainy afternoon, then we remember a rainy afternoon, which has sound, which has vision, which has space, which has time, all together. So Badley's third major idea is that this episodic buffer is where this kind of integration happens. And then it commits some part of it to long-term memory. And to do the task, it also has to retrieve something from long-term memory. And to control all of these things that's happening across these subsystems, we have the central executive. And see this, the arrows are bidirectional all the time. So here is information that central executive is sending. It's also information that central executive is getting. So you can technically move from phonological loop via the central executive or via the episodic buffer to visuospatial sketchpad. You can move from visuospatial sketchpad via the episodic buffer or the central executive to the phonological loop. It enables us to move information across all these subsystems in a flexible manner for us to achieve the idea of storage of information. Okay, to recap, three different models. One model is the simplistic model, which is a store-based model, and that is the three stores model by Atkinson and Schifrin. Sorry, here. Okay, we talked about what is stored, how much of it is stored in these kinds of things, using experiments of Sperling for sensory store, and the difference between partial report and full report, importance of the queue, things about how much is stored in short-term memory, and things about how much is stored in long-term memory, and the idea of chunking. And this is the second kind of memory model where they treat memory as a process, not as a store. They think that how much is stored is based on the level of processing involved at the encoding stage. And here there are three different examples of levels of processing that we have talked about. Physical, which is at a very superficial stage, phonological, slightly more deeper stage, semantic, deepest stage of processing. And then I talked about an integrated model of Badley, where he has integrated the visual part with the verbal part with the long term, and introduced two new things, which is the Visual Spatial Sketchpad and the phonological loop, and integrated all of them using an episodic buffer. Okay, I will skip details about each of this, but they are there in the slide in case you want to go through that. But I'll go to how you measure it, because measurement becomes, I think, a predominant part of what makes something a science. And if psychology is supposed to be a science, then it has to have well-defined measurements. And that's thankfully true for working memory, not true for many other things. But for working memory, this is how people have measured it. This is called an n-back task, which means that I show you one digit after another randomly. This is over time. So this slide comes, then this slide comes, and this slide comes, and likewise. Your task is n back. This n can change. So if it's a one back task, whenever you see a repetition, so you see a 6 and then you again see a 6, then you press a key on your keyboard, noting that one position back, I saw the same thing. A 2 back task is to say that 2 positions back, I saw the same thing. A 4 back task is to say 4 positions back, I saw the same thing. Now what you have to notice is that for one back task, it is cognitively least demanding, because you only have to store one item of information, which is your previous information. For 2 back task, it is cognitively more demanding, because now you have to store two items of information. For 4 back task, likewise, it is most difficult, because you have to store 4 items in your working memory to be able to notice that this is a repetition, which is after the fourth, at the fourth position again. Now, those who are able to do 2 back memory task is thought to have lesser working memory capacity than those who can do well in the 4 back memory task. So how much more amount of information you are able to store is a measure of your working memory. That's one way people have measured it. The second way people have measured is called the span task, where you will essentially be shown these multiple digits one after another, and then you have to reproduce the order. 5372 must be said as 5372, not 5732. And now this is again a measure of working memory. How long the span can be, how many random digits can you remember and reproduce in the same order is the digit span that you have. Somebody who has a 4-digit span has lesser working memory capacity than somebody which has a 7 or 8-digit span. Okay, now why is this important? It turns out that, and this is from empirical research, that those who score high on working memory tasks also show higher general intelligence. They're also able to perform better on different kinds of action, coordinated motor action, like driving. It has also been shown to be predicting certain domain-specific intelligences, like financial consulting. And it has been shown to also correlate with certain things like GPA and ability to learn and do good in courses. Now, please note that it's not always the case. You should not, the take home should not be that if I have lower working memory, I will not be able to do good in my coursework or be able to learn things or show general intelligence. There is some prediction, but which means that if I have higher working memory, then most probably I will also show higher performance in certain other tasks. But that does not mean that if I do not have higher working memory, I will for sure fail in these tasks. So don't take this too seriously. Last slide. This is how people have categorized memory. So one large scale categorization is by saying some of the memory types are declarative and some of the memory types are non-declarative. So declarative memory is of two kinds. One, you store facts. Like in the last class, we were saying, what is the capital of India? Is a fact, a semantics. A word itself is also a semantics. So that is stored in declarative memory. You also store an episode, like an afternoon, a rainy afternoon, or the first day at IIT. The whole day is an episode, or a very small instance of maybe something happened to you in a flick of a second, or 5 seconds. Episodes can be very short, episodes can be very long. But episodic means the whole event is one single memory. So both of these two kinds are declarative memory. Because you can declare, you can talk about them, you can write about them. Non-declarative memory is the opposite of that. You can't talk about it easily, you can't write about it. One example of procedural memory we saw was motor skills, which are procedural memory or procedural skills about how you can tie a shoelace or how you can tie a tie or how you are able to drive. It's very, or even how you are able to walk. Another example of non-declarative is something which is at a lower level of consciousness. So most of the priming work or the implicit memory work essentially says something about non-declarative. You can't really declare it, but you can act on it. Then other things about habituation and sensitization, which is you start habituating to a certain room temperature, for example, or you start habituating to a certain sound, or you start habituating to even a certain environment or certain food habits or certain, temporal time timetables of your day, but you can't really easily, put them in sentences. You act on it. Certain times you feel hungry, certain times you feel tired, sometimes you feel sleepy, but it's hard to really put them into words. Why exactly, or what is the content, or what's the knowledge that is leading you to feel a certain state like hunger or thirsty or tired or sleepy. So most of these, all of these stuff come under the non-declarative memory. These are memories, by the way. I don't know if any of you thought of these as memories before, but these are memories. But these are different kind of memories that we can't really declare or talk about. The other kind is declarative, which we are able to easily talk about. Okay, so I'll stop here. If you have any questions, you can ask. Yeah, for today's class, or also in any previous questions. And we conclude memory here. I mean, this is not too much of information. I'm giving you information that you can hopefully digest well without feeding into too much. But I also want you to understand whatever you're understanding well and not forget about it. Talking of forgetting.
Sir, like when we try to learn a definition of something, we tend to forget some of the words. Like even if we are reading a paragraph and we have to recall that, even if we are given like a whole day, then also we sometimes tend to forget some of the words. Like, is there a way of seeing which words we tend to forget, or how are we forgetting one word while recalling just
So
the previous one?
Purvi, right?
Yes, sir.
Yeah. Because you raised this, I was just wondering whether I should say a little bit about forgetting. Let me do that. So first of all, forgetting is good. The way society presents forgetting is bad. We feel embarrassed that we forget things. We are negatively reinforced when we forget things by giving less marks or by scolding and all. But I personally think forgetting is really helpful. Imagine a world, or even your brain, if you would not be able to forget. Most people will just go crazy. So first and foremost is forgetting is good, and whatever most of the thing that happens to us naturally is actually good. Otherwise, it would stop happening. I mean, this is an evolutionary story that whatever has worked out is what has stayed, right? So forgetting is something that has been helpful. So probably that's why it's there, because it reduces less important information and, and attenuates many other kinds of information in general. Now, why do we forget? Well, essentially, there are two models of forgetting predominantly, but there could be other reasons, and we can talk about that. One is we generally forget everything because this is more like, the metaphor of a capacitor. You store charge in a capacitor, it keeps on decaying. So we are forgetting all the time, every single day, every single moment of our life. So there's a general decay happening, and that's how you can think of capacitor. There's the other thing, and this is a pictorial representation of that. This is not a linear decay. This is typically a non-linear decay, as what happens with capacitor. And in fact, people have measured memory decay or memory or forgetting, and they found this graph, which also shows that how important psychophysics is. The physical way in which memory works is very similar to the way some of the um, electronic circuits or electrical circuits, not electrical circuits work, like capacitors. Similar kinds of decay happens in our brain. Okay, there's one more which I have not put on the slide easily, but there's another kind of decay that happens, which happens due to um, you know um, intervention. So once you already learned something, whenever new information is coming in, that creates an interference with the previously held information. So there are two processes happening. One is continuously we are forgetting some things and as a general decay process. The other is because new information is being learned, it is overriding the previously learned information. Or sometimes even if it does not override, it at least interacts with it. That interaction also fades certain other information which was previously stored. So certain kinds of stuff we will forget. Number one, it is based on how important that information is. So the probability of recall or the probability of forgetting is also value laden. We don't forget everything. We forget certain things which has minimum value for us. So if you are reading a paragraph, to coming to your answer now, if you want reading a paragraph, there are certain words that you're forgetting. Either the words are of low frequency, which means that they are more novel, so you have not really rehearsed them well and hence you're forgetting, or the words are interfering with common words that you use a lot or learn a lot or have encountered during the day a lot. The third possibility is you are forgetting simply because those words don't hold value for you, or a mix and match of both, all the three.
But sir, sometimes it happens that we forget one of the keywords, and even we remember its meaning, but we forget the word.
Mm-hmm.
So
That's
shouldn't it
probably because
we
of the first
should
one. That is because of very low frequency. So maybe that's a word that you're. Is it a word that you're learning new, like a new terminology or new jargon or something?
might be not, but sometimes we maybe it was used like some words are used two to three times in the paragraph, but we still tend to forget that word. And when we are recalling, we recall the meaning that yes, there was a word which meant that, but we can't recall the word.
Yeah, my hunch would be that for low frequency words, because that typically happens when you are not yet accustomed to the syllogism of the word, which is your phonological loop is not tuned to how the word sounds. And many a times it happens when we are learning new things, new jargons always. We somehow remember it, and that I see in many examination papers. Probably you all experience that when you write an exam. You somehow remember what it means, but you just cannot remember the word itself. And you get penalized because faculty is perhaps looking out for that word, or even you are looking out for that word, but it's just not there. But the meaning is there, which means that you know the if you think about it from a level of processing model, there hasn't been enough depth of processing. You somehow perhaps encoded it at the phonological level, which is what once you lose it, you just lose it. It probably has not got yet to the semantic level. You can understand a certain thing because you are understanding it with reference to many other concepts that you already know well or remember well. But that concept alone, you might not be able to understand. Whenever we, when we learn and read all through our lives, we are always trying to assimilate to things that we already know. That's why we have this progression. Otherwise, you can directly enter fourth year, right? The whole point of starting in class 1 is to build up over previous knowledge. And the way the brain works is it keeps on integrating new knowledge with already existing knowledge. And that assimilation, some people do it well, some people can't do it. Sometimes you can't even do it because there are big jumps in learning. But most other places, typically we try to integrate new knowledge with existing knowledge for us to feel better about it at the end of the day, but also to achieve certain functional roles, including passing of examinations or doing good in a job or really going about leading life or even traveling to a new location or driving a new road, whatever might be the goal. We always need to do this kind of an assimilation process.
That's it. Like there can be other words which are used in like less frequency, and we have heard about them for the first time. But still, we forget only one particular word. Like my question was, why is that? Is there a way to determine which word we are forgetting?
um, I don't know how you would do that a priori. I mean, if there's an example, then probably we can think about it. But it's hard to say which is the word that you will forget beforehand, if that's the one that you're asking. You can do, I mean, this is now at the top of my head, so it might not be very well thought about. But I believe we can handle this thing by, let's say you give a paragraph to read to 1,000 people, and you tell that those 1,000 people to reproduce the same paragraph. Okay, from that can now work as my training data to come up to a computational model that predicts low probability and high probability of recall for each of the words. That's doable.
Okay.
There are these natural language processing models that try to understand how difficult a text is to read. And one way that they understand, that they come up with this difficulty score, is by looking at the frequency of words from their database. What does the frequency mean? This is essentially a proxy of whether people are going to be able to either understand or remember these kinds of things, along with whether and how much that is used in common vocabulary. So if there is a paragraph and there are certain words that all are forgetting, then clearly there is something characteristic about that word or that concept. But if it is completely random, different people are forgetting different words, then this computational modeling approach will fail. I mean, then we have to think what are peculiarities for why somebody is remembering and other person is not remembering, which is a little more harder to do. All right, so one more quick point before we break today. Also, this is a very important thing. So the pace of learning, is very important. If you start learning too many things one after another, then it's not a great idea. The better eventual outcome happens when you have spaced out events, which means that you have one event, you forget some things about that event, then you have event 2. So it will result in more slower learning process, but actually the amount of learning that's going to happen is going to be superior. This is also why I was asking your opinions about breaks between classes, and also about whether it's a good idea to have the single paper all through the day versus multiple papers all through the day. So these are things that we will cover or take up in more detail during the tutorial, where we'll start thinking about, not tutorial, I mean, these are stuff that is interesting, and I have a reading material which I will share about studying and remembering for students and forgetting for students, which I think many of you will personally find it amusing and also helpful to accommodate or use some part of it for your own life.
Sir, one
Okay.
last question.
Yes, go ahead.
Sir, my question was that how do we forget some things and then recall them again? For example, there is something that I have already forgotten, maybe some friend's name from after watching a picture of them, and then I'm trying to recall and recall. I am not able to recall, but after a few minutes, I am able to tell the name. So if we have forgotten it, then how do we recall it? And if we are able to recall it, then why are we not able to do it quickly?
Yeah. Wonderful question. So see, the thing is, this is the same thing that, well, not same thing, this is a similar thing that Sperling also said, right? There are stuff that is there in our head, but we cannot recall it. It happens for very simple things like sensory storage, but it also happens for more complex things like a concept or a name. Now, why does that happen? Many a times it's dependent on the cue that is used to recall. It's probable that the cue that you were using to recall was not working. It is also quite possible that a later cue that you're using to recall, or you are perhaps not even using it, cues can also be activated on its own. Maybe you are doing something else, some other concept comes to your head, or you see something that then works as a trigger, as a cue for recalling this word or name that you're trying to find. So this is possible because we have a massively interconnected semantic network in our head. If you search semantic network, you will get these different kinds of computational models. In fact, one on which Google search initially started on, where you store this as a very big graph. And once you have a very big graph, you can have multiple paths to reach a certain node, right? So whichever path gets activated in your memory can lead to that same node. Maybe the path that gets activated at certain point in time when you are not able to recollect is what is not leading you to that path. But some other part gets activated after some other point in time, and that leads you to the same node. This is does this make sense? I mean, I can Google up. I don't have a picture, but let me see if I can show you. Yeah, so this is how a semantic network is like. You think of mammal as a concept which is connected to another concept called vertebra, and here you have a function, a relationship. Mammal has vertebra. Cat is another concept which is again connected to the mammal. Cat is a mammal. And likewise, you can think of your whole brain being connected in multiple complex ways like this. So if I had to remember the word, let's say vertebra, maybe I was ending up thinking about animal, and I was not being able to recollect the word vertebra because I was not able to go to vertebra. Right? It could also be something like this, where you don't necessarily have arrows. You may or may not have arrows. They also have weights because this is modeled based on how the human brain is. So here you have different other concepts related to certain other concepts, and what is related to which concept is weighted by how much important this connection is. So more important connections will have more weight, less important connections will have less weight. And then this can be having multiple loops in between. So that's why you can reach from one node to the other in multiple ways. Now this is how you can think about traversing this graph and also checking for certain declarative memory or declarative knowledge. Like, how do you know that Tom is a cat? So you first find Tom. Okay, Tom. Isa is a relationship to a cat, so Tom is a cat. This is typically done a lot in AI, but this is also very similar to what happens in human brains. And in fact, the AI models are heavily biologically inspired models, which is meaning that they borrowed these ideas from human neuroscience and psychology. Okay, guys, so I will stop here today and I will upload the slides and I will send also this PDF of the book, and we'll cover the decision making or the judgment part little later. It's running little late because I really think it's important for you all to understand what we are talking about in class instead of just putting in so much information in front of you.
Sir,